Alright, so this video is over something called static equilibrium. Alright, static equilibrium. Okay, so what does that mean, static equilibrium? Okay, so static equilibrium means that you are not accelerating. Your acceleration equals 0 meters per second squared. So that means something if you grab the ball and toss it up in the air, that is not in static equilibrium because that has an acceleration of 9.8 meters per second. So here we're talking about something that does not have an acceleration. So if we're talking about forces here, we know that F equals m times a, right? Force equals mass times acceleration from Newton's second law. So if we take acceleration and we put it in here, that means your force equals 0. Alright, so that means it's something in static equilibrium if it has no forces on it. Can you only have in a situation that has absolutely no forces and it not accelerate? Well, I think you can probably think of a situation where that's not the case. So what if we just had a table and we're going to have a box sitting on this table just like that? Okay, so what kind of forces do we have on the object? I'm sure you'd probably tell me that we have force of gravity going down, right? There's the force of gravity. And you'd also tell me that there's a normal force that's going up. So there you go, force normal. But this object is not accelerating. So how do these forces give you a 0 acceleration? Well, if you were to add them together, okay, if you were to add them together, force normal plus the force of gravity, okay, that would have to equal 0. It would have to equal mass times acceleration technically, but acceleration is 0 for this case, right? So what does that mean? That implies that the normal force is equal to the negative of the gravitational force, or vice versa. You can say the gravitational force is negative of the normal force. So what does that mean? What does this negative mean here in the equation? Well, the negative, just like any vector, just tells you direction. So this equation is saying that the normal equals the gravitational force in magnitude, but it is an opposite in direction. So the normal force is going up, gravitational force is going down. So they are equal and opposite. Now, not equal and opposite like Newton's third law, like we learned in class today. So the normal force and the gravitational force are equal and opposite. They do cancel each other out, and this equation says exactly that. Okay, so that means that in Newton's second law of F equals m times a, we can put more than one force here. We can put more than multiple forces as long as these forces are all acting in the same direction or in opposite directions, along the same dimension, like what we've had prior. So this is really talking about what we call a net force. Net force. What does net force mean? Well, it just means that all the forces added together, and this is what you have after you do that, your net force. So in this case, our net force is equal to 0. Okay, so not just one single force, but your net force equal to 0 for static equilibrium to occur. Net force equal to 0. All right, so let's try a different situation. Let's say we have a ceiling fan. Okay, so here's our ceiling fan. We got some nice blades coming off of it. Okay, look at me, I'm getting all artsy. All right, so we have the connection to the ceiling, right? So here's our ceiling fan. Hey, it looks like mine. So we have, what do we have in terms of forces on the ceiling fan? Well, again, we have force of gravity, right, coming down. I wouldn't call it a normal force here. We have a force that's pulling up on it from the ceiling, so we'll call it a force from the ceiling, and that's really a bad arrow. That arrow should be just about as long as gravity. In this case, we have that the force from the ceiling equals the force from gravity, and it's actually the negative force because it's in the opposite direction. So it's not moving, right? Not moving, not accelerating. We have static equilibrium. Okay. So the question, if this is static equilibrium, can we have equilibrium that's not static? What does the word static mean? Static is really what we're talking about here with not moving. So can you have equilibrium where it is moving? So that's still saying equilibrium is still saying that we have an acceleration equal to 0 meters per second squared, but does that mean you can't be moving? No, this just means that you have a constant velocity. And that constant velocity, well, it looks like an X, all right, just means that you have no force that's winning. So what about our Let's see. Let's say we have a block. Okay, we have a block that is being pulled from the side by a string that's attached to it. Okay, so this is a force from a string. Okay, can you imagine yourself pulling this across the table at a constant speed? Yeah, I'm sure you probably could. Okay, constant speed, not accelerating. So what are some of the other forces on this thing? We have force of gravity going down. We have our normal force, which is coming up. But the way that this looks like a box that's going to accelerate in the rightward direction. Okay, it's going to accelerate to the right because gravity is going to cancel out with the normal force, so those things are fine. But what's balancing out this force from the string if you're moving at a constant velocity? Well, you might convince yourself that if you're just dragging a box across the table, there's probably some friction that would also balance out. So in this case, your spring force, or it's not spring, your string force would be equal to the negative force of friction. This is equilibrium that's not static. Okay, equilibrium that's not static. So the forces still give you an acceleration of 0. Okay, another way of writing it again, force of friction plus the string force has to equal 0. Okay, so this is equilibrium that's not static. Okay, well, let's go back to static because static is much easier. So let's say we have a book. Maybe you're carrying I don't know, my physics book to class. Okay, and you're carrying it with both hands because it's just so heavy. All right, so there's one hand, there's another hand. Okay, nice hands. I'm going to make the hands a different color. Let's see what I have. Okay, I got a nice peach color. Okay, there's a hand, there's a hand. Okay, so your hands are balancing the book. They're taking the weight of the book. So if we drew a free body diagram of the book, okay, we would see a couple of things. First, we would see gravity going down, and we would see your hand pushing it up, right? But not just one hand, both hands. So there's a force from the hand, all right, and there's another force from the hand. So what does this mean? We still don't have it accelerating. It's not moving up, it's not moving down. So we have force from the hand plus force from the other hand plus the force of gravity has to equal 0. Okay, so that means 2 times the force of the hands, I'm just putting those together, right, plus the force of gravity equals 0. So what does this mean? That means the force from the hand is equal to a minus 1/2 the force of gravity. Look at that for a second. And that just means that, excuse me, that just means that your hand, each of your hands, is only taking half of the weight of the book. Well, that makes sense. You're using both of your hands. So this is still static equilibrium, but it's very nice, very straightforward. Everything equals 0, so we just have to balance out. All the forces going up have to balance all the forces going down, or vice versa. Okay, I'm going to leave you with one thing to think about. I want you to think about how a situation would look like this. What if you have something that's hanging on the wall, and it's hanging very weirdly. It's hanging by 2 strings, and these strings are going off like this. Okay, let's make that one a little bit straighter. All right, so we have one string here, call it S1. We have one string here, call it S2. And it's hanging on the wall. All right, so you know there's gravity going down. So how do you think that you might want to attack this situation if you know it's in static equilibrium that has no acceleration? Okay, I'm going to leave that for a question in the video, and I will actually put it there this time. You guys have fun.